Welcome to the session on variable acceleration using integration. The objectives for this session are to use integration to solve kinematic problems. Let's recall the rule for differentiating x to the power n. This is displayed on your screen. The rule for integrating x to the power n is the reverse of this. And this is now also displayed on your screen. Let's look at these two rules in diagrams. Integration is, of course, the reverse of differentiation. So when we're differentiating, if we start with x to the power n, we multiply by the power, so this now becomes nx to the power n, and then we subtract 1 from the power to give us nx to the power n minus 1. For the integration process, if we start with x to the power n, we first add 1 to the power, so we have x to the power n plus 1, and then divide by that power to obtain x to the power n plus 1 over n plus 1. So these here are our functions, and these are our gradient functions. We're now going to take a look at displacement, velocity, and acceleration, and see how they relate to each other in terms of integration and differentiation. So first, let's take a look at displacement. Suppose displacement s of t is a function of time. Then velocity v of t is ds dt, since velocity is the change in displacement over change in time. And acceleration, a of t, is dv dt, or this can also be expressed as d2s dt squared, since acceleration is the change in velocity over change in time. So if we begin with displacement s of t, we differentiate to obtain velocity v of t, or this can be of course expressed as ds dt. And if we differentiate again, this can either be written as dv dt or d2s dt squared, and this is of course the acceleration a of t. Now the reverse of this, say if we begin with acceleration a of t, we can integrate now to obtain v of t equals integral a dt, and then if we integrate velocity, then we obtain displacement. So s of t equals the integral of v dt. So to summarize, s of t equals the integral of v dt, velocity v of t equals ds dt, or v of t equals integral a dt, and acceleration is dv dt, which equals d2s dt squared. Let's now apply these formulae to an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's have a go at example 1a first. A particle moves in a straight line so that its velocity is given by v equals 4t squared minus 3 for t greater than or equal to 0. Its displacement s is measured from a point O. Given that s equals 4 when t equals 0, find an expression for the displacement of the particle at time t seconds. So let's solve this. We have that s equals the integral of v dt, which is of course, for our example, integral 4t squared minus 3 dt. Therefore, if we integrate, we obtain s equals 4 over 3 t cubed minus 3t plus the constant of integration c. Now, since s equals 4 when t equals 0, if we plug these values into our equation for s, as shown here, we obtain c equals 4. And therefore, s equals 4 over 3 t cubed minus 3t plus 4. And now for part B. We are required to find s when t equals 9, given that s equals 4 when t equals 0. So let's solve this. From part A, we have the equation for s as shown on your screen. So therefore, when t equals 9, we plug that into our equation as shown, and this gives us that s equals 13. And now for part C. We are required to find an expression for the acceleration a of the particle at time t seconds. So let's solve this. Now a of t equals dv dt. Therefore, since v equals 4t squared minus 3, if we differentiate v, we obtain a equals 8t. Now let's take a look at graphs. Recall that the area under the velocity time graph represents the displacement. Let's apply this to an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. A particle moves in a straight line so that after t seconds, its velocity is given by v equals 6 minus t squared for t greater than or equal to 0. Find the distance travelled by the particle in the 4th second of its motion. Before we use definite integration, check that v doesn't change sign in the interval being considered. So let's use a sketch to help us. Here's a sketch of v equals 6 minus t squared. We're looking in the interval between 3 and 4. Here, the distance travelled is the area under the velocity time graph. We need to use definite integration to find this. Now s of t equals the integral of v with respect to t. So in our example, this is integral 6 minus t squared dt, and we're looking between the limits 3 and 4. So therefore, if we integrate, we obtain this expression here. So 6t minus t cubed over 3 between the limits 3 and 4. So plugging these values in, t equals 4 here, and t equals 3 here, we obtain minus 6 1/3. This minus is actually consistent with the diagram we have on our screen, because this is the value below the x-axis, or this area is below the x-axis. So velocity is negative, and therefore the displacement is negative. The example asks for the distance travelled. So when we answer the question, we need to give a positive value. And therefore, the distance travelled is equal to 6 1/3 meters. This brings us to the end of this session. If you have understood its contents, you should be able to use integration to solve kinematic problems. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.